for a spherical resistor, we can say, well, let's say that we want to find the resistance for a spherical resistor with inner radius A and outer radius B. Conductivity rho. This one actually turns out to be a little easier to do than that tapered resistor one. If we draw the picture of it here, here's our inner, so we want the resistance from here to there. So this is like a conducting medium with a hole in the middle. So it's got an inner radius A and an outer radius B. We want to know what the resistance to current flow is if the current is flowing out in a spherically symmetric fashion from that, which is really pretty similar to the problem we just looked at, except that it's through a whole sphere instead of a hemisphere. And so we can do that is we can say, well, if dr is rho dl over A, then dl is the little tiny bit of distance that the current moves as it expands. So your dl here would be a dr, because the current is moving in the radial direction. So therefore, this little dl is a dr, the little element of radius of this spherical shell that has an inner radius A and outer radius B. Okay, and so we could write then our resistance then is the integral of rho dr over, and now because it's a full-on sphere, the area of that surface is the area that the current is moving through as a function of r. So that's going to be 4 pi r squared, the surface area of a sphere. And so that gives us then rho over 4 pi times minus 1 over r. We integrated 1 over r squared to give us minus 1 over r, evaluated from A to B. And so that'll be rho over 4 pi, and then I just reverse the order of integration to get rid of the minus sign. So this is going to be rho over 4 pi times 1 over A minus 1 over B. So that would be the total resistance. Just by doing a relatively straightforward integration, where we're just saying, okay, each one of these little shells that has a thickness dr is contributing a little bit of resistance to the total resistance of the spherical shell. We can go back to the previous page and see, well, how does that relate to what we had before up here? Well, we had rho over 2 pi times 1 over b minus 1 over a. Here it's rho over 4 pi times 1 over b minus 1 over a. So from that we can see that this is the resistance of the hemisphere. And it's twice as big because all the current had to go out through the bottom half. Okay, but it's the same as this. If we just look at this, this is V equals IR. And so that's exactly what we have here, except here we let the current go through the upper half as well as the lower half. Since we have double the area, we have half the resistance. Here we have double the resistance, so it's over 2 pi instead of over 4 pi. But It's essentially just another way of looking at that same problem as an Ohm's law problem, V equals IR. But with a resistance, that depends on how far you move through and also the geometry of the conductor. Any questions about that? Got one more of these. This one's with a tapered resistor. I'll let you look at this one after I pass out a copy of this in lab, and then we can go over this one early next week. But what I want to allow enough time for here is for you to work on our group quiz. Reminder that our group quiz won't contain any of the stuff that we covered today, but there'll be a good concentration of materials that involve Gauss's law and the principle of electric potential. So in this first problem, we have a spherical shell that has an inner radius A and an outer radius B. And we have a charge density rho within that spherical shell that goes like A over R. Then in the center, we've got a charge, point charge. And they give you values for the point charge and the charge density. Well, they give you everything except A. And so what we want here, and this is kind of an interesting problem, is what value should A have if the density here, it's going to be, it's A over R. That means it's more dense in here and less dense out here in terms of the charge density. So we have more charge concentrated toward the middle and less charge out toward the outside. So we want to know from this, you go, well, what if R equals 0? Well, you don't get to R equals 0 because the inner radius is A, so you can avoid that problem. The inner radius of this thing is not 0 because there's a point charge in the center, and the insulating sphere doesn't start until A. So the insulating sphere is from A to B. So what we want then is the value of A so that we have a constant electric field in this region between A and B. So what you're going to want to do is, here's your A value, here's your B value, and then you've got a charge in here. You know this charge in here is going to produce an electric field that points that way. And so that means that if you go out to some radius R, you're going to want to have some kind of a contribution that makes up for the fact that you're moving farther away from the center. So you want the electric field of those two together to be a constant. Now the way to do that is, we know that the integral of E dot dA is equal to Q enclosed over epsilon naught. Okay, so the charge that we enclose then is going to be the central charge, I'll call Q naught here, and the charge that is from A to R. Okay, so Q enclosed is going to equal Q naught, that's the center charge, plus the integral of rho d volume. Because the density changes as 1 over R. So rho is equal to A over R. And so the charge that we enclose here has to be the result of the sum of the charge that's in the center plus the charge that is enclosed by this Gaussian surface. And the charge that's enclosed by the Gaussian surface, remember that rho is dq d volume. So rho times d volume is equal to dq. So the little bit of charge then that we get for a dr here, we add all those together from r equals a to b. And then the d volume is what? For a sphere. Good. 4 pi r squared dr. If you don't believe that, remember that volume for a sphere is 4/3 pi r cubed. So dv dr is 4 pi r squared. That's the surface area of the sphere. So dv is 4 pi r squared dr. So you don't need double integrals or anything for that, triple integrals. Not necessary. You just take, because it's a uniform in the radial direction, you can write it as a function of r, and then you include the fact that this is a over r times 4 pi r squared dr. You integrate this from a to b, so you want the electric field to be a constant. And so that means it can have a dependence on r. So that means that you want your r factors to cancel. So that's problem 1. And then in problem 2, we've got a negative charged ring with a positive charge in the center, and we want the point A where the total voltage is 0. Because this is similar to what we did before with electric field. Remember, we figured out where the electric field would be 0 from a point charge in a charged ring. But now you need to write the expression for the voltage for a negative charged ring. And then add that to the voltage for a point charge, and then find the condition on x, the distance, that gives you a 0 voltage at that point. Okay, so we've got help for you here. Both of our embedded tutors are here to help. And so this will be due on Tuesday. And you might easily see something like this as one of the quiz questions for sure.